Hello, everybody. Good morning and welcome to class 36, the last class of Physics 131 this semester. Of course, there's Physics 132, which will start up in January. Same kind of thing, same book, just continuing on with at Kina. Different professor, though. You'll be with Professor Seelfen, very good friend of mine, fantastic teacher, who's taught me a lot, actually, about teaching. She'll be taking over. Right now, she's your practicals coordinator. Just to give you the idea here of, take a look at my screen too. We've got course review, a liquid nitrogen demonstration. There's a final bonus team up quiz, which is hopefully you guys can see that. Just check my chat. There's also, I put there a little news article yesterday on the CBC. Health Canada approves the Pfizer BioNTech COVID-19 vaccine. So I kind of feel like this is, maybe this is all going to end next year at some point. We'll all get vaccinated, be immune. So there's going to be, I think what I want to do is talk about the final assessment and maybe do a little practice. You're going to be able to find it on Quarkus under a new module called Final Assessment, which is there now. The format is a 30-minute multiple choice test followed by a 10-minute break and then a 35-minute 2-question written answer assignment to be submitted on CrowdMark. And somebody asked me last time how they're weighted. Half of your final assessment mark will come from the multiple choice, those 10 questions, and the other half will come from the written answer part, which is marked out as 16, but they'll be scaled so they'll both be worth the same amount. And the timing goes like that. Starts at 7:10 p.m. on Thursday, December 17th. So it's a week from today. I think that's it. So what I've done is I've posted the rubric for these 5 possible chapters, so you can take a look at that right now. Actually, on the Quarkus. Some stuff going on in the chat window, just people chatting about what's going on with the vaccine and stuff and allergic reactions. It's going to be, I think maybe 2020 was like the year of this virus, and 2021 is going to be the year of the vaccine, trying to figure out how we're going to get the vaccine and which vaccine and all that stuff. And I heard that Ontario is going to be issuing like vaccination cards, to show that to prove like if your photo ID, so that I guess you can get into stores and stuff like that. It's going to be a weird year for sure. Yeah, Carol Zhao was asking if our final grade lands on a 0.5 or above, will it be bumped up to the next percentage? Yeah, I can only submit an integer to the grades on Acorn. So like if you got 89.5, then that would be rounded up to a 90, for example. And yeah, that's the same for all courses, I think. Let me stop the share, because what I want to do is actually move things around a little bit and show you right now the liquid nitrogen demonstration. I'm a little anxious to do that. So actually, you can see what's going on here is I've got a train here. I've got some liquid nitrogen. When you're working with liquid nitrogen, it's good to put on, I can see you guys in the chat window still up there. So you can alert me if anything weird is going on. Yep. Hi. So what I've got is, I'll put on my gloves here, is I've got a dewar full of liquid nitrogen, which is Pius has produced for me. So what it is it's air, which is cooled down to 77 degrees above absolute zero, which is the boiling point of nitrogen. So it looks like water, but it's boiling. It's nitrogen that's boiling because it's right at its own boiling temperature. And then, so that's it. It's kind of just cold stuff, and pour it out if you want it. You don't want to drink it. It's very, very cold. You don't want to touch it because you can get burned, and you don't want to touch anything that's touching it. And what I've gotten here actually are these little pellets. I was going to also pour some in here as well. So we'll try. This is a pellet of what's called yttrium barium cupric oxide. And if you put it on a magnet, it'll actually float there. So what I can do is try to put the camera down so you can sort of see what's going on there. See the little floating magnet going along? Whoop. Don't be shy. Dip Cheetos in it. You could do that. Yeah, so this is just what it does. This is called the Meissner effect, which is that it becomes magnetic when it's superconducting. So this thing will levitate until it starts to warm up and then it falls. You have to cool it so that it becomes a superconductor below its critical temperature, which is about 100 degrees Kelvin. So when it gets down to 77, it's cold enough to be superconducting, expelling all magnetic fields around it, and then it kind of levitates on its own little magnet there. I can also put it on a magnet. Another strong magnet there, which I can put it in here again. It keeps on warming up. I think I might have a better, put that there. One thing at a time here. Dip it in. And put it on here. And now you can kind of see how it sticks there. And I can kind of, that fell off. I push it on a little bit and it sort of sticks and doesn't want to fall off. Whoa. I don't have any solid nitrogen. Okay, I want to see it sort of more up close. So that's kind of how it works there. And there's nothing up my sleeve. I think I have another one actually where it's doesn't fall quite as fast. Use the tongs to get that out here. This one. This has got a yttrium barium cupric oxide superconductor sitting inside it, and but it's also encased in sort of a foamy thing. So that one, again, I think you can even sort of turn it upside down. And so it's actually, well, it's draining the nitrogen in there, but it's pulling as well as pushing. It's locking the magnetic field in at that particular distance. So that's kind of a cool thing. And then the other thing that we can do, so I'll just leave that there and see how long it stays there. When you can see, maybe I can show you that there's no like tricks up my sleeve or something like that. It's really just actually levitating there. It's kind of a cool thing. Cool, get it? Okay. So that's that. The other thing I can do is I have a rose. So does anyone here want me to dip the rose in the liquid nitrogen? Yes, okay, Lauren. All right, so I'm gonna do it. Not a nice thing to do to a rose. We might as well try it, see what happens here. Oh, it's really boiling as it, because the rose is at room temperature, obviously, which is boiling off a lot of the nitrogen. Let's see what it looks like. Pull it out of there. So this is a very cold rose now. Oh. See, it's already kind of flaking away and becoming brittle. And of course, I'm making a big mess with that table there. So we can try that. Sort of smashes. Okay. I think that's it. Made a little bit of a mess. Sorry about that, Pius. I'm sure you're in there kind of going, what is he doing? But we'll clean that up a little bit after. Hey there, Physics 131. This is the extra bonus video for chapter or for class 36, in which I'm just going to go over 3 more written questions, which I had sort of been planning to do today, but I didn't quite get to it. So I'm just doing this for YouTube only. This is the showing the rubric for chapter 9 questions on rotational motion. And there's lots of different kinds. It gets a little more vague in chapter 9, 10, and 11 because there's a lot of different representations you can do. But basically, let's just do one. Imagine that our sun ran out of nuclear fuel and collapsed, which is actually going to happen in only about 5 billion years, probably. What would its radius have to be in order for its period of rotation to be the same as the first discovered pulsar, PSR B1919 plus 21, which has a period of a rotational period of 1.34 seconds. So this is a conservation of angular momentum, so conserve rotational momentum. And that's because there's going to be no external torques. So you have to draw then the initial and the final situations. So the initial is that the sun is kind of big. It has some R initial, which I would have to look up, but I can do that. I've looked it up on Wikipedia. The radius of the sun is 6.96 times 10 to the 8 meters. So it's quite large, 696 million meters or 696,000 kilometers, much bigger than the Earth. And then it has a T initial of 25 days. That's the rotational period of the sun. And then finally, if it shrinks down, it'll have some R final, which we don't know, and a T final is going to be 1.34 seconds. So the system is the sun. So assume that there's no external torques on the sun. So what that means is that L initial equals L final. So that's just how I would write that. And so I would just say, I wouldn't do any bar diagrams or anything, but basically L is equal to I times omega is rotational momentum. And the rotational momentum stays the same if there's no external, I guess, torque impulse or rotational impulse or something like that, which is certainly the case. So M is constant. And we can also, I should put it here somewhere here, is that assume, we might as well assume the sun is a solid sphere. So we'll have to look that up as well, but I got I is equal to, I think it's 2/5 mr squared. Put that little aside here. I don't think it's going to matter, but assuming that it keeps the same sort of shape as it shrinks, then what you've got is L initial equals L final. L initial is going to be I initial times omega initial is equal to, and the other thing we need to know is that omega is equal to 2 pi over period, right? I final, omega final. We are asked about period, so we can right now convert that to I initial times 2 pi over period initial is equal to I final times 2 pi over period final. We can just divide both sides by 2 pi, I guess, if we want to get rid of that. And then we can also use this equation for rotational inertia, and we end up with 2/5 of the mass times R initial squared over T initial is equal to 2/5 m times R final squared over T final. And again, we can divide both sides by a constant. There's the mass is the same as it shrinks, is the assumption there, and 2/5 goes away. So you just end up, we can solve kind of rearrange that, solve for, we're trying to find R final. So R final is equal to R initial times the square root of T final divided by T initial. So R final is equal to that 6.96 times 10 to the power 8 meters times the square root of 1.34 seconds divided by 25 times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And I get 5.5 times 10 to the power 5 meters. So to put that into terms, if we change to kilometers, we divide by 1,000. So 5 minus 3 is 2, so it's 550 kilometers. And that's pretty small for a star. And in fact, it's about the size, maybe a little smaller, of a white dwarf star, which is what the sun will become when it shrinks down and runs out of hydrogen at the core. Okay. Chapter 10, Vibrational Motion. Again, kind of vague here, but you state your assumptions and represent the process. Okay, so if necessary, you might have to use these simple harmonic motion kinematics equations. You might have to use force diagrams. You might have to use work energy principles, maybe some energy bar charts. It sort of depends on the problem. But let's just do one particular problem. Let's say that you attach a 1.6 kilogram object to a spring and pull it down from equilibrium position and let it vibrate. So I think they're talking here about a vertical spring, mass hanging from a spring. Mass is equal to 1.6 kilograms. Pull it down 1.3 meters from its equilibrium position and let it vibrate. So what that means is that A equals 0.13 meters. That's amplitude of simple harmonic motion. Okay. Because it's going to go again up and down around equilibrium. And then the period, T is equal to 5 seconds divided by 10, 5.0 seconds divided by 10 vibrations. And it's trying to find what is the spring constant of the spring. So that's, we're just going to assume SHM, no dissipative forces. I guess we could say that the system maybe is the mass, something like that. So anyway, we just use that the period for mass in a spring is equal to 2 pi times the square root of m divided by k, and solve for k, because we have all those things, right? So 2 pi over, t over 2 pi is the square root of m over k. So just square both sides, and we get t squared is equal to 4 pi squared is equal to m over k. T squared over 4 squared equals m over k. Solve it for k. I get k is equal to 4 pi squared times m divided by t squared. So k is equal to 4 times pi squared times 1.6 kilograms divided by 0.5 seconds. Sort of did this in my head here. If it's 5 seconds to complete 10 vibrations, then the period is half a second. So squared. So I got, plugging that all into my calculator, I got k is equal to 250. I'm going to put it into SI units, newtons per meter. A strong spring. And how do you evaluate this? I don't know. You could also say as m, it goes up, stiffer spring is needed or something like that. M is on the numerator there. That kind of is another way to evaluate sort of a limiting case. And then lastly, chapter 11 on mechanical waves. So same sort of thing. It's going to depend on what's going on in each question, what you do here in steps 2 and 3. You represent the problem using mathematical relationships. So it could be, there's a lot of different little parts, but let's just do a Doppler question today, and then I'll be done. A car horn vibrates at a frequency of 250 hertz. Determine the frequency a stationary observer hears as the car approaches her at a speed, typo there, of 25 meters per second. So the car is now moving and beeping, beep, and sending out this wave, and it's going. So it's moving at some Vs is equal to 25 meters per second towards the observer. VO is 0, it's just sitting there. F of the source is equal to 250 hertz. F of the observer is equal to question mark. That's basically it. We're assuming here that Doppler shift will cause a slight increase in the frequency. Will cause frequency to increase slightly. So instead of 250 hertz, you might hear 260 hertz or something like that. That's my kind of guess. Let's use V is equal to 340 meters per second is the wave speed. Speed of sound. And hopefully on the final assessment, I would actually give you that equation. You can use 340 if it's not there. So we're going to use equation 11.15 from Etkina, but it's for the toward version. So when it's toward, it's a little higher. So you want the denominator to be a little lower. So you're going to use the minus sign. Use minus sign in the denominator. And the way I remember to do that is that I need it to be a little bit bigger than the frequency. FO is equal to Fs times V over V. V is the speed of sound. Vs is the 25. You're going to minus it off the bottom. That way your denominator is a little less than 1 or a little bit less than V, and then you're going to get a number that's going to be a little higher. So you're going to start with the 250 hertz and times it by 340 divided by 340 minus 25. And I got 270 hertz is the observed frequency. And again, makes sense as it is a little higher. And that's it. A little higher pitch because the horn is coming towards her. Okay, that's it. There's something that you should be able to see right now on your Quarkus called Team Up Quiz Bonus Course Review. Your pod team shares the mark. So right now what I want you to do is open up your Microsoft Teams and somebody place a video call to the members of your pod chat so you can see each other, hear each other, and chat about this team up. First step is to decide who will be the team up driver. And then everyone logs into Quarkus and you know the routine. Drivers have to start a new session and share the session ID with everyone else in your Microsoft Teams chat. Non-drivers, once you get that, you join that session so that everyone in your little room there, in your call, arrives in the team up. And then you can start going through the questions. There are 4 questions today, which I'll go over in about 15 minutes. Let me put on my timer for 15 minutes here. I'm going to put myself on mute. Annie makes a good question there. Should we keep our calculators in radian or degree for the final? I think the safest thing is to keep it in degree mode, but you have to be careful. You might have to have it be able to switch it to radians mode. You almost always use degrees, though, I think, in this course. It's just this waves business. You want to go over question 1? This is the steel square frame. People didn't do so well in this on midterm 5, so I thought I'd go over it a little. 1 meter by 1 meter in size, and it weighs a total of 4 kilograms, can be thought of as 4 connected steel bars. So what I think is, for the sides one, I side, just use that it's mass times r squared, where this is the distance right here, right? Distance from the rotation axis. And r is equal to 0.5. So it's equal to 1 kilogram times 0.5 squared. So it's 0.25. And then the top, this is, you have to actually go to the to that table, and it's 1/12, I think, of m times l squared, where l is the length of the thing. When you've got a bar that's rotated around the center, it's 1/12. Yeah, Faison asked a question. The rotational stuff is in radians per second and stuff, but you don't often type cos or sine for it. So I guess that's why you don't really need to switch your calculator to that. So it's going to be equal to 1/12 of 1 kilogram times 1 meter squared. Anyway, it's a 12th. It's 0.0833 repeating. And so the I total, there's 2 of the sides. So it's 0.25 plus 0.25 plus 0.083 plus 0.083 for all the 4 sides. When I added it all up, I got 0.67 kilograms meters squared. So I guess that rounds to B. And Joshua, that's a really good point. For questions like this, if it's on the exam, I will try to remember to give you that rotational inertia equation. But it might be good to know where, put a post-it note on it in case I forget. And so, and Dima, good question. So for the sides, what I'm doing there is I'm just using all the mass. When all the mass is at the same distance from the rotation axis, it's just mr squared, and there's no factor out in front. You only use these factors, like a 12th, if you've got a shape which is rotating around, so that different parts of the shape are at different distances from the rotation axis. And that's top in the end, sorry, I bottom, same. They're the same, right? Should we go over, a couple questions on the chat. Jerry?
Yeah, hello, Prof. Yes, since midterm, I have this question, but I never had a chance to ask. For those kind of rotational inertia, why is it that for the mass on the side, don't use the formula?
Because all the mass is the same distance from the rotation axis. It's like a point, right?
Okay. So whenever there's like a point,
every point on this object is at the same distance from the rotation axis, r. So it's just the sum of all these masses times r.
So we treat them like a hoop.
Yeah, like a hoop, yeah. Because that's the same with the hoop. Hoop is the same thing. Every point on a hoop is the same distance from the rotation axis.
Oh, okay. I see. Thank you, sir.
Yeah, you're welcome. And Ethan?
So the way I did the problem is that I just use 1/12 ml square and then put 4 kg as the mass. Why did that not work? And 1 meter as the L.
Well, because you've also got the edges, I think, right?
Oh, but what doesn't 1/12 account for the entire rectangle? At least
well, if it was filled in, yeah, it would be. If it was a solid rectangle, then yeah, you just use 1/12. But this is a steel frame, so so for the outer edges here, all the mass is concentrated at a distance of 0.5 meters from the center. Whereas if you had what you're suggesting, like a filled-in rectangle, then it would be spread all over those different distances.
So in the context of this question, what does the 1/12 ml squares represent? Like the top and...
Yeah, just the top and the bottom only.
Can you explain why that is?
Because those are the objects that have mass at different distances from the rotation axis, right?
Yeah.
Anytime you have an object where it's got some of its mass spread out at different distances from the rotation axis, then you have to go to that table. But If it's oriented in such a way that all the mass is at the same distance from the rotation axis, then you just use mr squared. You don't need any fraction.
Oh, okay. Yeah, got it. Thank you.
Yeah, you're welcome. Question 2, a stationary bike has a wheel that rotates while its axis of rotation does not move. The wheel has angular acceleration is constant. Okay. Which of the following statements is true? The magnitudes of AT and A, so basically AT is going to be R times alpha at the edge of the wheel or something is a constant. Ethan, do you want to put yourself back on mute? And AR is equal to V squared over R, where V is equal to omega times R is changing. That's right. So that's not true. Which one's right? Magnitude of the tangential acceleration is changing with time. That's not true. Magnitude of the tangential, is constant, but the magnitude of the radial acceleration is changing with time. So as V increases, then that will increase. Does that make sense? Question 3, Earth's orbit around the sun has the same major axis of, so this was something we did a little while ago. This is Kepler's law. You remember that one? Which is Kepler's third law, which is that T squared divided by R cubed equals K. This is equation 5.5 from page, I think it's page 137. So what you can do, it's the same constant for any planets. So T1 squared over R1 cubed is going to be equal to T2 squared over R2 cubed. And you can rearrange that and get that R2 is equal to R1 times, I guess, the cube root of T2 over T1 squared. So it's going to be the 1.5 times 10 to the 8 times the cube root. So you have to find cube root on your calculator of 1.6 divided by 3.2, which is the half squared. So you square a half, cube root it. What I got was 0.95 times 10 to the 8 meters. Interesting. And I'll save these and put them up on the screen. And then the last one was the thing that messed you guys up way back on midterm 1. You walk half the distance to school. So here's your, let's switch to blue, I guess. Or here's your D over 2, and your V1 is equal to 1.0 meters per second. You go that far. And then here's your D over 2, and you go V2 is 4 meters per second. So what you're going to do here is V average is just equal to D divided by T1 plus T2. But the problem is you don't know T1 and T2. So what you're going to do is say that V1 is equal to D over 2 divided by T1. You can solve that out. So what that means is that T1 is equal to D over 2 times V1. And then V2 is equal to D over 2 divided by T2. So that means that T2 is equal to D over 2V2, right? Anyway, you guys can do it, right? So V average is equal to D divided by all this stuff, D over 2V1 plus D over 2V2. So the D's all cancel at this point. You have to divide top and bottom by D. You'll get that V average is equal to 1 divided by 1 over 2 times 1 plus 1 over 2 times 4. It's equal to 1 over like a half, 0.5, plus an eighth, which is 0.125, right? I got 1.6. That should have been pretty simple for you guys. It's just an old style kinematics question. You know what? I'm going to stay on this call for a half hour just to chat with anyone who wants to hang around. But I think that's pretty much a wrap for me. It's been a weird one, hasn't it? Single strangest class. You guys were my first Zoom call for teaching. And so I appreciate your patience with me for the whole semester as, you know, I figured this out. Somebody told me about Snapchat, so I put it on my phone. No idea how it works. You know, I'm so out of it. Maybe I'm just a little old for this. I am almost 49 years old, so that's probably the reason. Don't forget to do course evaluations. Please email me if you got any questions. You can either that's my actual personal email address, or you can email the Physics 131 Fall that goes through April, and then she can deal with a lot of stuff as well. Keep in touch, and maybe when this whole COVID's over and we all have our little vaccination cards or whatever, we can get together in my office and you can come by and say hi. So it's it's been great. I'm gonna turn off the record and then see if anyone has some chat. So bye everybody, bye. Have a great break, and hope to see you around.